the last class. Now, what are the main points we discussed in the wave motion? I will revise it clearly. Please follow this. So, wave motion means here in this topic we will discuss about sound. Sound is a form of energy. Sound is a form of energy. What we discussed in the last class. We know different forms of energies are there, like light energy, chemical energy, and mechanical energy, and so on. Electrical energy. So many different forms of energies are there. Sound is also just a form of energy. And this sound will travel in the form of waves. So, the sound travels in the form of waves. Sound travels in the form of mechanical waves. Sound travels in the form of mechanical waves. What is a mechanical wave means? We have different types of waves, that what we discussed in the last class. We have different types of waves, like mechanical waves, electromagnetic waves, and matter waves. These mechanical waves will require a material medium for its propagation. So, here see this. These mechanical waves require a material medium for its propagation, whereas electromagnetic waves, they doesn't require any medium for its propagation. Like if you take electromagnetic waves means light. Light doesn't require any medium for its propagation, right? Because it is an electromagnetic wave. But sound requires a medium for its propagation. The basic reason for it is a mechanical wave. So keep in your mind, a mechanical wave requires a medium for its propagation. Mechanical wave requires a material medium for its propagation. It requires a material medium for propagation. For its propagation. And also we discussed that this material medium must have the properties of elasticity. The properties of the medium must be, the medium should have the properties of, medium should have the properties of elasticity and inertia. Elasticity and inertia means any medium which has high elastic and inertial properties can easily allow the sound wave. Means it easily propagates the sound if it has high elastic and inertial properties. So, if you compare, generally the matters are of three types. We have solid substances, we have liquids and gases. If you consider solid, liquids and gases, generally the solids will have high elastic properties and inertial properties when compared to liquids and gases. Thereby, sound can easily, which is a mechanical wave, it easily travels through this medium, solids. It can easily travels through solids. Why? Because the solids will have high elastic and inertial properties. Therefore, we can write the velocity of sound in solids is always greater than velocity of liquids, and is also greater than the velocity of gases. In turn, it is gases. So, simply saying, velocity of sound is more in denser medium when compared to that of velocity of sound in a rarer medium. A denser means high density. Like solids will have more density when compared to liquids and gases. So velocity of sound is more in denser medium when compared to that of a rarer medium. For example, if you take a steel and velocity of sound in steel is more when compared to velocity of sound in water or velocity of sound in air. So sound will travel through air with minimum speed when compared to that. Okay, now you keep this, just it is an introduction that what we discussed in the last class. For the newcomers, I have given this. So these are some important points. So finally keep in your mind, sound is a form of energy. It travels in the form of mechanical waves. As it is a mechanical wave, it requires a medium for its propagation, and the medium should have the properties of elasticity and inertia. Velocity of sound is more in denser medium when compared to rarer medium. So in a similar way, we can discuss like this. Some other points we discussed, I'll explain again. So here we learned about different types of sounds also, how a sound is produced. Generally, sound is produced, all vibrating bodies produces sound. Means when you struck any body, when you struck a tuning fork, a sound is produced. When you struck any body during vibrations, it produces the sound. So keep in your mind, all vibrating bodies produces sound, but some are audible sounds, some sounds are not audible. So I will explain what are infrasonic sounds, which is the inaudible. This is not audible. Infrasonic sounds are not audible to us. What are infrasonic sounds means? They will have a frequency less than 20 Hz, and ultrasonic sounds will have a frequency greater than 20,000 Hz. Means the infrasonic sounds having a frequency less than 20 Hz are not audible. They are not audible. And ultrasonic sounds which are having a frequency greater than 20,000 Hz also not audible. So now come to this. What are the audible sounds? Audible frequency range. Audible frequency range. If you consider the audible frequency range is it is 20 Hz to 20,000 Hz. The audible frequency range is 20 Hz to 20,000 Hz. Means if you produce a sound which is having a frequency in between 20 Hz and 20,000 Hz, then it is audible to all. So keep in your mind, this is audible frequency range. Another important point is wave velocity. Wave velocity can be written as, according to the formula, wave velocity can be written as V is equal to n lambda, where n is the frequency of the sound and lambda is the wavelength of sound. So if you want to calculate the frequency using this formula, the frequency can be written as V by lambda. I want to calculate, okay, n is equal to V by lambda, or you can calculate the wavelength. Lambda is equal to V by n. So keep this very important. If you want to calculate the wavelength range, use this formula, lambda is equal to V by n. So I want to find out audible wavelength range. What is the audible wavelength range is, audible wavelength range I want to determine. So I want to find out what is the maximum wavelength that is audible. The maximum wavelength that is audible can be written as V by the minimum frequency. What is the velocity of sound generally? Velocity of sound in air medium, it is nearly about 330 meters per second or 340 meters per second. So lambda maximum can be written as V by m. Generally the velocity of sound in air medium at STP conditions is nearly it is 330 or 340 meters per second. Now the velocity of sound, if you consider this as 340 by the minimum frequency is 20 Hz, so you will get it is about 17 meters is the maximum wavelength of sound that is audible. Similarly, the minimum wavelength of sound can be calculated by substituting the maximum frequency here. Therefore, it is 340 by 20,000. If you calculate this, so you will get about 17 into 10 power minus 3 meters, or it is equivalent to 17 mm, or it is equal to 1.7 centimeters. So the wavelength range is also important. Audible wavelength range is, we can finally write the audible wavelength range is, it is from 17 into 10 power minus 3 meters. It is the minimum audible wavelength. What is maximum audible wavelength is nearly about 17 meters when only if you consider the velocity of sound as 340 meters per second. So this is what we discussed already, but it is only for the newcomers. Just it is simple to understand and keep in your mind. The audible frequency range is 20 Hz to 20,000 Hz, and the wavelength range is, it is how to calculate the wavelength range. It value depends upon, wavelength range value depends on velocity of sound in that air medium. Okay, frequency doesn't depend on the velocity of sound or anything, the medium properties, but the wavelength of audible wavelength range depends on velocity of sound here. Keep in your mind, and this is the wavelength range. Okay, then I will continue this. Now again I have explained about what happens during wave motion, and we have discussed about the types of waves also and the phase concept. I will explain them again now. Just listen, right? What happens during wave motion? Keep in your mind. Very, very important. I will write the important point during wave motion, but I will explain in a simple manner. To explain this wave motion, okay, I want to explain this within just 2 minutes of time. Okay, I will mention what are the main important points in this. First I will write the points. See, the wave motion means here when a wave is propagating through air medium, what happens means, main points are, first I will write, then I will explain. Both energy and momentum, transfer of energy and momentum takes place. Transfer of energy and momentum takes place from one place to another place. From one place to another place. From one place to another place in a medium. Right? See that both energy and momentum transfers from one place to another place. And another thing is, all the medium particles during this propagation of the wave, all the medium particles executes SHM. All the medium particles executes SHM with same time period, with same amplitude and time period. Okay, time period. These are the very, very important points during wave motion. So now for that I had given a small example. Just I'll explain this. Right? See this. When a sound is produced in the air medium, what happens is, say I have produced some sound here. The sound will travel through the air medium. All the medium particles here in front of me, air particles, are subjected to vibrations. Okay, means during vibrations, a compressions and alternatively compressions and rarefactions are formed in the medium. Means the disturbance created here will travel forward in the form of compressions and rarefactions. What is meant by compression means all the molecules of the air comes closer to each other during compression, and due to elastic nature again they will move back. Means the distance between the molecules increases. That is called as rarefaction. During compression all the air molecules will come closer. During rarefaction they move away from each other. So while vibrating, the medium particles are vibrating like this. While vibrating, what happens? Compression is formed here. After some time, a rarefaction is also formed due to vibration. Say this is one particle, this is another particle. They are vibrating like this. While they are vibrating, what is happening? The distance between them is decreasing. Means they come very close to each other. Again, they move away from each other. So this is the concept. But what is happening is, while vibrating, see that the particles will not move from one place to another place. While they are vibrating, the compressions and rarefactions are forming, right, alternatively. And while they are vibrating, they do not leave their original position. At the same position, they are at the main position, but they are vibrating to and fro about that rest position. During these vibrations, what happens? The energy will be transferred from one particle to another particle. So, if one air particle starts vibrations, neighboring particle also starts vibrations. Means, in this way, energy transfer takes place. All the medium particles executes SHM. Means, all the air medium particles, suppose if you consider this is air, right? If you have taken a tuning fork, when you struck a tuning fork, what happens? When you struck it, the air particles will move to and fro about this. Means first they are vibrating like this. All these air particles will vibrate. This is air particle, say neighboring air particle. So this is also vibrating. All these air particles are vibrating to and fro about their rest position. While when they are vibrating, they comes closer and they moves away. Means what happened? The energy will be transferred from one particle to another particle. If it starts vibrating, neighboring particle also starts vibrating. So it transfers energy to the neighboring particle. Now it starts vibrating. So the energy transfer takes place in this direction. Transfer of energy is there because we struck the tuning fork here. We have created some disturbance here. That disturbance is now traveling from left to right. It is the direction of propagation of energy, and the medium particles are also vibrating in the same direction. They are vibrating parallel to the propagation of energy. But during that, what happened? Compressions and rarefactions are developed. While they are coming closer to each other, what is formed here? A compression is formed. When here, if it is a compression is formed in this region, they are moving away from each other. Means here what is formed? A rarefaction is formed. So alternatively, during vibrations, if in this region compression is formed, immediate region in the neighborhood, we will find a rarefaction. Means alternatively, compressions and rarefactions are formed. So energy transfers in the form of compressions and rarefactions. This is the important point. So finally, keep in your mind, very simple point. If you produce some sound in air medium, the air medium particles, the particles of this air medium, they start executing SHM. They are vibrating about their main position. While they are vibrating, they transfer their energy to the neighboring particle. As a result, what happens? Both energy and momentum is transferred from one place to another place. and all the medium particles are executing SHM with same amplitude and time period. And this type of propagation of energy in which the medium particles are vibrating in the same direction of propagation of energy is known as longitudinal progressive wave. What is a longitudinal progressive wave? See that, longitudinal progressive wave. What is meant by longitudinal progressive wave? Progressive wave means the name itself, progressive. It proceeds into the medium. Once the disturbance is created, it continuously proceeds into the medium without any reflection. A wave which proceeds into the medium, which travels into the medium without any reflection is known as a progressive wave. But the sound energy which is propagating through air is longitudinal. Why? Because all the medium particles are vibrating parallel to the direction of propagation of energy. Thereby, this propagation of energy is known as longitudinal progressive wave. So, this is about the best example for longitudinal progressive wave is, what is the example for propagation means, here the example for longitudinal progressive wave is the propagation of sound in air. Propagation of sound in air medium. Propagation of sound in air medium is the best example for longitudinal wave propagation. And according to the definition, can I define this longitudinal wave? In a longitudinal wave, all the medium particles vibrate in the direction of propagation of energy. Okay, is it clear? So, now I would like to explain. So, finally, keep in your mind what happens during wave motion. During wave motion, both energy and momentum transverse from one place to another place. Okay, all the medium particles executing SHM, right? All the medium particles executes SHM. We know that. Any particle which is executing SHM can be represented with the equation y is equal to a sin omega t plus or minus phi. I will come to this later. But before that, we learned about, already I had explained about transverse wave. What is a transverse wave? For that I had given one example there already. So it is a stretched string. It is a string which is stretched in between 2 points. It is a stretched string. A wire is stretched. Say this is a wire and it is stretched means it is rigidly fixed here at the 2 points. If you hold this wire at the middle and when you stretch, after stretching to this level, when you plug the wire, means the position of this particle after stretching, it will comes to this place, right? When it is right. Now this will be the wave, right? This will be the position of the wire. Means all the particle. If you name this particle A, it will be here now. But the neighboring particle, when it is stretched, this neighboring particle will reach to this place, right? This particle will reach to this place. Okay. So like that, all these particles are stretched to this level. When it is stretched like this, then after when you release it, what happens? Due to elastic nature, this is the position of the wire. When you release it, it will move down. It will vibrate. This particle will try to regain its original position. Originally it is at A. Now it is stretched to this level. After release, it will move in the backward direction. After reaching to this position, its velocity becomes maximum. So that then now it will move down. And it reaches to the another extreme position. Means if you see this particle is moving up and down. It is moving. This becomes the mean position. This becomes the positive extreme end. And this becomes the negative extreme end. Similar way, as it is starts vibrating, the neighboring particle also starts vibrating. It is moving up and down. See that? All of them will complete one vibration in the same time. All of them will complete one vibration in the same. If it completes one vibration, it will also complete one vibration in the same time. Means all these particles means starts vibrating, means energy transfer takes place from A to B and B to C and C to D, like this. This is the direction of propagation of energy, but the string particles are vibrating in up and down. Means see that the direction of vibration of the string particles are at right angles to the propagation of energy. So this type of means, now this will be the shape of the means. When you observe that string, we will find a loop. We are finding a loop means all the particles are executing SHM. Now, as they are executing SHM and they are vibrating in a direction perpendicular to the propagation of energy, this propagation of energy or this wave is known as transverse wave. In a transverse wave, what happened? Now, if the same wire, we can make the same wire, it can be vibrated with more number of loops. We can make it to vibrate with more number of loops. Means when you stretch the wire here, you will get a wave like this. This wave will travel forward like this and reaches this point. When the wave travels like this, here, if you see, this is the crest and this is the trough. This is a crest and this is a trough. So, a crest is formed here and another crest is formed here because this is the trough. Right. A complete wave means, what is meant by a complete wave? Complete wave means a crest and a trough. This will form a complete wave. And this is another wave. Like that. A complete wave means a crest and a trough is known as a complete wave and its length is known as wavelength. Length of the complete wave is known as wavelength. This is the length of the wave. This is the length of the wave. This is called wavelength. And here another trough is formed. Again, wavelength can also be defined as it is the distance between successive crests. And also it can also be defined as it is the distance between successive troughs. You can define the wavelength like this. The distance between successive crests or the distance between successive troughs. So we can define the wavelength with the help of this crests and troughs. In a longitudinal wave also, there in the longitudinal wave, what are formed? Compressions and rarefactions are formed. Suppose if it is a compression, here in this region if a compression is formed, suppose here a rarefaction is formed, again another compression, means alternative compressions and rarefactions are formed. The distance between successive compressions is known as wavelength. Or the distance between successive rarefactions is also known as, means a compression we can represent like this, not required, right? This is a rarefaction. So the distance between successive compressions is lambda, distance between successive rarefaction is also lambda. So finally, keep in your mind, what are the important points in a transverse wave? In a transverse wave, important point is, here the particles of the medium vibrate in a direction perpendicular to the propagation of energy. Second one is alternative crests and troughs are formed. Okay, means simply saying it travels in the form of crest and troughs. The distance between successive crests or troughs are known as successive crests or successive troughs are known as wavelength. Okay, so these are all the medium particles, means like this, all the string particles, all the medium particles executes SHM with the same amplitude and time period. Okay, so we can define like this, and this is about transverse wave. And the best example for transverse wave is, what is the example for a transverse wave is, the best example for a transverse wave is the propagation of light energy. Light. The propagation of light is the best example. Propagation of light. Why? Because light is purely transverse in nature. Light energy is purely transverse. It doesn't have any longitudinal components. Means light energy always propagates in a direction perpendicular to both electric and magnetic fields that you have learned in the electromagnetic wave theory. Maxwell's electromagnetic wave theory indicates that if you stretch your fingers in mutually perpendicular directions like this, if this indicates the direction of propagation of light energy, means electromagnetic wave. Light energy is an electromagnetic wave. If it indicates the direction of propagation of light energy in mutually perpendicular directions, means in this plane, in this direction, in the direction of central finger, if electric field is developed, here a magnetic field will be produced. Means there will be variations in the electric and magnetic fields. Okay. So light energy propagates always in a direction perpendicular to the mutually perpendicular electric and magnetic fields. So energy propagation is perpendicular to the electric and magnetic field vibrations. Okay. So that it is always energy propagates in a direction perpendicular to the electric and magnetic fields. So it is purely transverse. It doesn't have any longitudinal component. So the basic difference between sound and light is, sound is a mechanical wave. Okay? Sound is a mechanical wave. It exhibits all the properties of light. It exhibits all the properties of light except polarization. This is also very important. Sound doesn't exhibit polarization, but sound can be reflected, sound can be transmitted, it will diffract, interference. We can discuss about all these properties, but sound doesn't exhibit polarization, whereas light it exhibits polarization. Why? Because the basic reason for it is